Flow instabilities occur everywhere. They affect most of the flow phenomena we encounter. We shall first look at several examples of flow instability and try to find out what they have in common. Then, we will examine one flow instability in more detail. The flow instability you just saw was produced by a drop of cream into water. Smoke rises because it is lighter than the surrounding air. The smoke plume is steady near its source. Further up, waves occur, the plume becomes unstable, then turbulent. Instability is the first step in the chain of events which generate turbulence. A capillary jet of water from a tap may be stable and smooth, or unstable and buckle, depending upon its length. Not all flow instabilities result in a new unsteady flow. For example, let us look at the flow between two concentric cylinders. The inner cylinder turns, the outer cylinder is stationary. We have put flakes in the fluid to make the flow visible. Turning the inner cylinder at an angular velocity less than a certain critical value, the flow is stable. Increasing the angular velocity to above critical, bands appear in the flow. If we put beads in the fluid, we see that the bands are really toroidal vortices. If we increase the angular velocity still further beyond the second critical value, a second instability occurs, and at still higher angular velocities, the flow becomes turbulent. This tank contains two fluids of different densities. Disturbing the equilibrium, we see waves on the interface. When the lower fluid is flowing to the right, the upper fluid will have to travel to the left to fill up the space. At the interface, near the middle of the tank, there is a velocity shear. Such a shear interface between two fluids of different densities is unstable under certain conditions. For larger shear amplitude, we see little waves appear at the interface. They are a result of shear instability, often called Kelvin-Helmholtz instability. At still larger amplitudes of velocity shear, the waves will break, resulting in the confusion you see here. So far, we have seen that there is a critical condition associated with flow instability. Using this wind tunnel, we shall examine one flow instability in more detail, show its critical condition, and attempt to extract some more of the general features of flow instability. Air blowing over a liquid surface often excites waves. This is a flow instability. In this tunnel, we blow air over a mixture of glycerin and water. Room air enters the tunnel, flows through the test section, and is sucked out by these vacuum cleaners. We can control the airspeed and we can put disturbances into the fluid. At zero airspeed, a disturbance damps out quickly. At low airspeed, it still damps out. At this higher airspeed, if we put in a disturbance, waves appear and grow. At even higher airspeed, waves seem to appear spontaneously and grow. The flow is unstable. We don't understand all the characteristics of this instability phenomenon, but I have chosen it because it is visible and because it contains many of the general features of instability phenomena. Now, let us explore its characteristics. The waves contain energy. They get their energy supply from the airstream. Where do these waves come from? They are triggered by accidental disturbances in the airstream. These disturbances contain all wavelengths, but only a certain range of wavelengths are amplified. We can picture the mechanism of flow instability as a frequency-selective amplifier and picture it as a black box, although this is really oversimplified. An amplifier needs an energy supply. This amplifier takes its energy from the airstream. The amplifier input is any disturbance that happens to come along. This could be upstream turbulence, noise, or an intentional disturbance we put in. The output is damped or amplified waves. When the amplification ratio, the gain, exceeds unity, we have instability. The amplifier gain varies with frequency and also depends upon flow parameters. In order to find the frequency response of amplification, we put in sinusoidal disturbances which we can control. We start the wave maker oscillating at 5 cycles per second. At zero airspeed, the waves are damped as they travel away from the wave maker. With the tunnel running, but below critical airspeed, we don't notice much change in wave damping. As we increase the airspeed and pass critical speed, we see the waves grow. Let us now look quantitatively. We measure the height of the waves using a capacitive transducer and record the wave height and airspeed on this pen recorder. Now the wave maker is going at a constant frequency and amplitude. Using a motor drive on the airspeed control, we start the tunnel and then increase the airspeed slowly. We can speed this up cinematographically. Here is the record. I put it up on this frequency wind speed diagram. We see that at this wind speed the wave amplitude is small, while at this higher wind speed the wave amplitude is large. Waves of this frequency start being amplified about here. Let us repeat this at a higher frequency. Again we see that at low wind speed the wave amplitude is small, and that beyond a certain wind speed the wave amplitude grows. If we repeat this experiment at other frequencies, a pattern becomes apparent. We can draw a curve through the points where we first get amplification. The neutral curve. Outside this curve, the waves are damped. In a region inside the curve, the waves are amplified. We can also do the experiment the other way. We keep the wind speed constant and vary the frequency. The records go this way on our diagram. They fit our curve. We can also draw contours of constant amplification. They look something like this. Our experiment has yielded the characteristics of the instability. What happens without the wave generator? Then accidental disturbances trigger the instability, and the first amplified waves will be in this frequency range at this wind speed, the critical wind speed. So we have seen that there is such a critical wind speed. We do have a selective amplifier, and the amplified frequency band does vary with wind speed. Now let us mention some of the physical processes which enter into the mechanism of instability. The airstream provides the wave energy. From a fixed frame of reference, we see the wind and the waves move. The wind speed exceeds the wave speed, and the average current is 0. And now, in a frame of reference moving with a wave, the wave phase speed is of course 0. The wind speed is less in this frame, while the water is moving to the left. It is the relative wind velocity which determines the pressure on the waves. The pressure will be low at the crests and high in the troughs. This distribution of pressure tends to increase the wave height, were it not for gravity and surface tension, which tend to flatten the waves. In this simplified view, if the pressure forces win, the waves will grow and we have instability. If gravity and surface tension win, the waves will decay and we have stability. This does not explain how we get energy transfer from the wind to the waves. As we know, waves of different wavelengths move at different phase speeds. A plot of phase speed against wavelength shows that for wavelengths beyond the very shortest waves, which are dominated by surface tension, the longer the wave, the higher its phase speed. waves of different wavelengths will feel different relative winds. A wave moving at the same speed as the wind will feel no relative wind and therefore no air pressure variation. This gives a clue as to why some waves are amplified and others are not. We have so far ignored viscosity and the existence of boundary layers, among other things. Here, in the coordinates of a wave, is what the average velocity profile looks like. The action of viscous and turbulent stresses across the critical layer will result in a change in the pressure distribution on the waves from that given by potential flow. The net result is to shift the pressure distribution to the right, and we see now how the pressures can do work on the waves, push them along, so to say. So we see that at a given airspeed, the lowest frequency waves will not feel enough relative wind to grow. An intermediate range will grow, and the very shortest high-frequency waves will again be damped. This particular instability is rather complicated and involves many flow parameters: Froude number, Weber number, Reynolds number, water depth measured in wavelengths, etc., etc. Now let us look at some other flow instabilities and describe them in terms of our block diagram. For each, we will indicate the energy supply, the critical flow parameters, or the dynamic processes involved. For some, we will also try to show you what happens beyond instability, namely transition to other instabilities or to turbulence. Here is a container with heavy fluid at the bottom and light fluid on top. I fill a small container with a heavier fluid and slowly raise it into the light fluid until the heavier fluid in the container is above the light fluid. I should expect this to be unstable, but it doesn't seem to be. If the interface is perturbed, for example by poking at it, the hydrostatic pressure will tend to increase here and tend to push it further down. But in this case, surface tension pulls the bulge back up. Surface tension wins the struggle with hydrostatic forces, if you like. We lower surface tension by injecting a few drops of surface active agent. And I will try a little more. The energy source for this instability is gravity potential. The critical parameter is this ratio, which measures the relative effect of gravity, scale, and surface tension. This is one of the Taylor instabilities. A fluid heated from below may become unstable. This thin cell contains fluid and particles to make the motions visible, and a heating element at the bottom. As we turn on the heat, the fluid becomes unstable. The hot, buoyant fluid can get away before it loses heat and buoyancy to its surroundings. The critical parameter is the Rayleigh number, which involves gravity, the thermal expansion coefficient, the vertical temperature gradient, and the effects which tend to prevent instability, viscosity and thermometric conductivity, and finally a length parameter h, such as the thickness of the fluid layer. Above a critical value of the Rayleigh number, a layer of fluid will be unstable. Here is a layer of fluid heated from below and cooled by the air above. I increase the Rayleigh number by heating the bottom. The time scale in this scene is speeded up. As the Rayleigh number goes beyond critical, instability sets in the form of Bernard cells. Let us look at that again. Adding a drop of shiny fluid at the corner of 3 cells, we see the fluid spread out along the bottom and come up again, showing the location of a cell as seen from below. If we now tilt the bottom of the pan, the Rayleigh number will vary across the pan because of the variation in depth. On the left, the layer is shallow, the Rayleigh number is below critical, the fluid is stable. In the middle, the Rayleigh number exceeds critical and the Bernard cells are apparent. Going further to the right, we see the size of the Bernard cells increase. Their size is proportional to fluid depth. You can see similar processes in the kitchen and also in nature, where clouds may be the visible trace of cellular convection patterns. A shear flow is often unstable, even in the absence of density differences. In this jet of water into water, shown by dye streak lines, the jet is surrounded by a shear layer. This shear layer goes unstable and waves appear. As they grow, they distort the streak lines. Next, secondary instabilities occur and then transition to turbulence. The instability is due to velocity shear, with Reynolds number as the critical parameter. A familiar example of flow instability is the flow around the cylinder. When the cylinder is moving through the fluid at less than critical Reynolds number, the flow around the cylinder is steady, although we can see a slight instability in the wake. Increasing the Reynolds number by increasing the velocity, the flow around the cylinder becomes unsteady. A vortex wake develops, the Kármán vortex street. Just below critical Reynolds number, the stability is precarious. A small accidental disturbance is enough to trigger large fluctuations. Let us look at that again. Steady, stable flow, the bubble, and here it goes. Now we run a larger cylinder. The Reynolds number is larger and above critical. The critical parameter is Reynolds number. It is this instability which makes telephone wires sing in the wind. As we have seen, a steady flow may become unsteady for certain ranges of flow parameters. The instability takes its energy from the mean flow and the mechanism can be thought of as a selective amplifier, its characteristics governed by flow parameters. Flow instabilities occur everywhere. Smoke from a stack billows. The flow in a river is turbulent. The turbulence is caused by flow instability. Air coming out of a pipe into water ascends in bubbles rather than in a steady stream. A flame may be unstable or stable depending upon the parameters. The weather is a manifestation of flow instability, both on the large and on the small scale. If we really look for it, we can see flow instability almost everywhere, along with the ultimate consequence, turbulence or random waves.